to turn this into a finished proof. Let's just add writing around our work that makes sure that the reader understands where all of our notation and variables and assumptions and all of our logic comes from, and also understands our overall proof strategy, how it is that we're going about this proof. So we'll begin by reminding the reader that because this is an if and only if statement, we need to prove two implications, the forward implication and the reverse implication. So we'll prove first that if 5 divides x, then 5 divides x squared. And then halfway down the proof, we'll say the opposite. Now, shifting gears, we'll prove that if 5 divides x squared, then 5 divides x. Now we'll fill in the logic that was on our napkins above my head for each of these two arguments. To prove that if 5 divides x, then 5 divides x squared, on our page over here, we used a direct proof, where we assumed the hypothesis and we deduced the conclusion. So we'll say, let x be a natural number, and let's assume that 5 divides x. Now we just need to get access to this line of algebra. X is equal to 5 times a, where when we did our scratch work, we remembered that a was supposed to represent an integer. But we can't just bring a into our proof unless we tell the reader what a is, where it comes from, and how we know that it exists. And how we know that this a exists, such that x is equal to 5a, is by the definition of divisibility. So we need to call the reader's attention to all of those things at once. We can do that by saying, by definition of divisibility, there exists an integer, a, so that x is equal to 5a. So notice what this sentence does. It tells us what new object that we're bringing onto the stage here, an integer a, right? And we know its relationship to the other players in our play here, x is equal to 5 times a. And the reason we know that that integer exists is that we provided this warrant. We've said by definition of divisibility. And if the reader is unclear of why that follows, they'll go and look up the definition of divisibility and just see that we're using divisibility by 5 directly from the definition right here to make this deduction. So now we've introduced a new player called a into our proof. We've said where it comes from, what properties it has, and how it's related to the other things that we know. So now we have x equals 5a. So we're at this point in our proof. And then we're supposed to begin the calculations, right? Now that I know that x is equal to 5 times a, I can say something about x squared. And we can more or less write these 3 lines as they are into our proof as calculation. Having done that, now we just need to sort of explain what this little arrow that I drew on the napkin means, right? We identified that x squared was equal to 5 times 5a squared. And the reason we liked that is that that 5a squared is supposed to fill in this blank to get us to where we're trying to go. X squared is equal to 5 times something. And this something that fills in this blank needs to be an integer so that we can satisfy the definition of divisibility of x squared by 5, right? By the definition of divisibility. So when we draw this arrow, we were reminding ourselves that 5a squared exactly fills in this blank, and that blank is the blank in the definition of divisibility by 5, so that blank has to be filled by an integer. Let's bring the reader into that conversation one step at a time. So what's important about the 5a squared? What's important about it, first of all, is that it is an integer. Now, how do we know that it's an integer? Well, we would know that 5a squared is an integer because we knew that a was an integer. And we knew that a was an integer because that's what the definition of divisibility gave us in the first place. It gave us this integer a to begin with. So we might say that in our proof by calling the reader's attention to the fact that 5a squared is an integer and why we know that 5a squared is an integer. So I'll write a sentence like this one. Since a is an integer, we know that 5a squared, which I'm going to give a new name, I'm going to call it b here, we know that b equals 5a squared is also an integer, and that x squared is equal to 5 times b, according to the calculation that we did above. Thus, by definition, we see, by definition of divisibility, we see that 5 divides x squared as desired. And that completes the forward implication of this proof. So now we've proven that if 5 divides x, then 5 divides x squared. And so now it's time for us to make the transition that's promised right here. We'll prove the other implication. If 5 divides x squared, then 5 divides x. So now we need to make sense of what's written on this right-hand napkin as a proof. So how are we going to do that? Well, notice that for this part of the argument, we did not use a direct proof approach. Instead, we used an indirect approach where we denied the consequent. Right? We took 5 divides x and we turned that around and said, let's see what happens if 5 were to not divide x. Then that broke out into a proof by 4 different cases, and in each of those 4 different cases we were able to deduce that 5 does not in fact divide x squared. So we have to do something up front here to tell the reader that we're going to use an indirect style of proof. So we'll say something like, suppose, by way of contradiction, that 5 does not divide x. So we put that there, again, to tip off the reader that we're not going to be making a direct argument for this piece. We're going to be making an indirect argument. And so the reader should be expecting, once they see this sentence, that what conclusion we need is going to be a denial of the antecedent. We need to show that 5 does not divide x squared. And just to help the reader, let's just say that that's going to be our strategy. We will show that then 5 does not divide x squared. 5 does not divide x squared. So again, we're tipping our hand to the strategy so that the reader knows where we're going with this so that they'll more easily be able to tell when we've gotten there. So now that we know that 5 does not divide x, we can break out into these 4 cases. Since 5 does not divide x, we may proceed by the following 4 cases. And then we will list out for the reader what those cases are. So you've set up the 4 different cases, and these 4 cases are exhaustive. We know that if x is not a multiple of 5, that it's going to have a remainder of 1, 2, 3, or 4 when it's divided by 5, necessarily. That's the Euclidean algorithm at work. So now we know what these 4 cases are. We just need to now step the reader through the logic that happens in each one of these cases. Remember, in each case, what we did was we took x squared, we expanded it out using algebra, and identified it as 5 times some integer, either plus 1 or plus 4, depending on which of the cases that we happen to be in. So this is a good place to sort of reproduce that algebra in each one of these cases. So in each case, we do out the algebra to figure out what x squared ends up being and showing that it's equal to 5 times some integer plus 1 or plus 4. Then we just need to draw the reader's attention to what's important about the quantities that are in these parentheses, namely that they are integers. And that's how we know that x squared is not divisible by 5, because x squared is equal to 5 times an integer, either plus 1 or plus 4. And so in each case, we end up saying something like, since m is an integer, so is this quantity inside the parentheses, which in this case was 5m squared plus 6m plus 1. And so we've shown that x squared is equal to 5 times an integer plus 4 in this example. So by definition of divisibility, 5 does not divide into x squared. And since we've done that for all 4 of our cases, and those cases exhaust all possibilities, we can conclude that if 5 does not divide x, then 5 does not divide x squared is true for all integers x. And that proves the reverse implication, which then concludes our proof. So there's a lot involved in translating from our napkin scratches into a formal written down proof. And that's a process that, especially when you have the time to write and to rewrite and to craft and to simplify your proofs so that they're maximally readable to your audience, it's always worth investing that time. Because sometimes in that process of translating, you figure out that there's something that you either could have said better or maybe something from your napkin that actually is a gap in your logic. So it's a really valuable place to catch not only stylistic choices that you can make when you write, but also potentially catch any mathematical errors or oversights that you might have had when you did the work a little bit less formally. And at the end of the day, what professional mathematicians do is they communicate with one another. It's not enough to kind of keep all of our thoughts and ideas and proofs in the informal sort of chicken scratch mode. That when it comes down to it, we have to have it on paper to communicate it out to others so that they'll not only be able to see that we've proven something, they can see exactly how we've proven that thing. And by retracing our own logical steps, they can learn more about not just that something is true, mathematically speaking, but why that thing must be true. And it gives them an insight into how we reason, And it's how mathematicians cultivate future mathematicians. And mathematicians in each subfield of mathematics have their own distinctive ways of thinking and reasoning and writing, and they help to cultivate experts in their own subfields over time as well as they read the proofs that are generated in that discipline. So this process of translation is not one to be taken lightly. And particularly when you have the time, if you're not trying to write a proof under time pressure on an exam or something like that, taking this extra time to really process a proof from the napkin form into a finished, polished form is worth your time. It really is part of developing professionally into your mathematical skin.